Here's an example problem for you now. You are pushing a heavy box across the carpet. The box has a mass of 30 kilograms. You push at a 30-degree angle downward to push the box. So you're pushing down on the box, like at some angle downward on the box to move it across the floor. You probably already know that that's not the best idea. The coefficient of kinetic friction is 0.4, which, that's not bad, that's not good either though. And you push the box at a constant speed. Use that clue to answer for me. You can type it in if you want, but you don't have to. What is the net force on the box if you're pushing the box at a constant speed? You can give me an exact answer, and that exact answer, that exact numerical answer is 0. Yeah, if you're pushing the box at constant speed, there's no acceleration, so the net force on the box has to be 0. That means that all the forces have to cancel out. It's not that there's no forces, it's that all the forces cancel with each other. And so the force that the ground is applying to the normal force, and the force of gravity, and the force of friction, and the force of you pushing on it, you take all the components of those in their respective directions and you add them up, and the total should be 0 to create 0 net force on the box. Do you think that the normal force on the box is going to be 30 kilograms times 9.8 meters per second squared? Is the normal force in this case going to be equal to mg? Well, we've got to remember, we're pushing down on that box as we push it across the floor. We're not pushing straight down, but we are pushing at a kind of an angle. Now, okay, if you're at your table, like we've been using as an example, imagine drawing a free body diagram just for the table with nothing on it. The floor is pushing up on the table with some force to keep it from falling through the floor. Well, now you start piling stuff on top of the table. If you put more and more stuff on top of the table, then the floor has to push up more on the table. You put more stuff on the table, and the table feels like it's getting heavier from the frame of reference of the floor at least. And so the floor has to push up more on the table to keep the table from falling through the floor. So pushing down on the table, if you push down on the table, the normal force on that table has to increase. If the normal force increases, well, then we're going to have consequences when it comes to the friction. But because we are pushing down at that downward angle on the box, it's actually going to have a greater normal force on it. You push down too hard and the box falls through the floor. But we're not going to deal with that kind of thing because, as I said, that's more material science. Right now, we're just going to deal with, if you push down more on the box, then the floor has to push up on the box more to counteract your downward push. So is the normal force on the box 30 kilograms times 9.8 meters per second squared? No, it is not. That's something that we might need to calculate. Well, the main question we're going to deal with here is, what is the force applied to keep the box moving at a constant speed? We're pushing down on the box at an angle of 30 degrees. The box has a mass of 30 kilograms. The coefficient of kinetic friction, because I did say it's moving at a constant speed, and if it's moving at a constant speed, then it has kinetic friction, 0.4 is the coefficient, which is not the force of friction. This is not the force of friction. The force of friction is mu times the normal force. So remember that. This is just the mu part of it. I can make a free body diagram right there. We've got the force of gravity pulling down. We've got the normal force preventing it from falling through the floor. We've got the force of friction saying, no, I don't really want to move. And we've got the force applied saying, yep, you're going to move. And we know that the acceleration in this particular problem is 0. So we can start with either x or y. I don't know what to start with. Let's just start with x because I wrote that down first. It doesn't really matter if you start with x or if you start with y. Start with one of them and work until you can't work anymore and then switch. You'll see that here actually. F net x is equal to max. The net force is all the positive forces in that direction minus all the negative forces in that direction. If you look at this right here, then this force applied has some in the x and some in the negative y. Like that, we can break up that force applied into those two components right there. We're looking for this amount, and we know that this angle in here is 30 degrees. And that gives us the clue we need to figure out the length of that. Well, that's going to be the applied force in the x direction there minus the force of friction there, because it's all the positives minus all the negatives, is equal to max. We know that ax is 0. And so I'm just going to replace that with 0 right there, because the acceleration in total is 0, because I said that it's moving at a constant speed. Fax is going to be Fa times the cosine of theta, because you can draw the triangles in there and do the SOHCAHTOA and everything, minus the force of friction, mu n. This is specifically mu k times n. Perhaps I should have specified that, but it is mu k times n. And we say, okay, force applied times the cosine of 30 is equal to mu times n. Now this is that weird case where the normal force is not equal to mg. I know a lot of people like just saying, oh yeah, normal force is equal to mg. But if you're pushing down on something, then take this piece of paper. Right now, there's not much normal force on that piece of paper. But if I push down on it, then the table is having to push up with more force to keep the paper from falling through the table. And so we don't know what the normal force is because we're pushing down at an angle on this box. So there's not really much more we can do here. Yeah, I guess we can figure out what cosine of 30 is. We could plug that in. We could plug in the 0.4 there. We've still got one equation and two unknowns. And we've got one equation and two unknowns. That means that we need another equation with those same unknowns to figure it out. And so, well, we did this for x. We've always got y that we can work on. And so F net y is equal to may. For the same reason, I'm going to say may is 0 because there's no acceleration in y. The box isn't like flying up. It's not diving into the table. So we take all of the positive forces minus all the negative forces. That's exactly what F net means. So all the positive forces in the y direction. We've got the normal force pointing up. We've got the force of gravity pointing down. And we've got this component of the force applied pointing down. And so we can take normal force, the positive one, minus all the negative ones. So minus Fay, the y component of Fa, the force applied, minus the force of gravity. And that should equal 0. And then do the same thing. We move some things around for our convenience. And we said that the normal force is equal to Fa sine 30 plus mg. You can see that normally the normal force is equal to mg. But in this case, the normal force is equal to mg and some other stuff. And that's because the floor has to be counteracting your push downward on the box in order for the box to not just fall through the floor. So that's where that comes from. Now we've got two equations and two unknowns. Here's an unknown, there's an unknown, there's an unknown, there's an unknown. We know the mass, we know gravity. We can ask our calculator what these things are. And so we need to find a way of, what are we searching for? We're just searching for the force applied. And so if we can solve for force applied, we've got it. Well, the way you solve for force applied is you solve for the other thing first, you solve for the normal, and then you plug that equation in wherever you see an n in that equation. So we can do that here. I recreate the two equations that we left off with on the previous page, that one and that one, and I say, okay, we've got n equals that stuff, we'll plug that stuff in for there, and we get FA cosine 30 is equal to mu times n, and we can plug in all the numbers that we've got in there. So cosine of 30 became 0.866, mu became 0.4, FA we still don't know in any case, sine 30 became 0.5, m times g, that's 30 times 9.8, that's 294, and then algebra that, and we get the force applied is 177 newtons. The question to begin all this was, at what force do I need to push in order for the acceleration to be 0 if I'm pushing at that 30-degree angle? And so the answer is, well, to push the box across the floor at 0 acceleration, I need to push with 177 newtons. Question for you, you're pushing a heavy box across the carpet. Do you want to push down harder or lift the box up a little bit? I think that anyone who's ever moved anything across anything knows that if it's a big heavy object, you don't really want to be pushing down on it to move it across the floor because it makes it more difficult. Whenever you move some big heavy thing, you probably either push it directly, like push it straight towards where you want it to go, or you lift up on it a little bit and you drag it across the floor. Lifting up is going to do the opposite as pushing down does. Pushing down artificially inflated the normal force on an object. And normal force, increasing the normal force is going to increase friction because friction is mu times the normal force. So if you artificially increase the normal force by pushing down on something, then you've increased friction. You can lower the normal force by pulling up on that object. If you've got some object and you pull up on it slightly, well, let's say you have a book on a table, and you just very gently pull up on that book, not enough to actually lift it off of the table. But if you're pulling up on it a little bit, then the table doesn't need to work as hard to support it. I'm using work very loosely in this sentence, but you can imagine that pulling up on the book means the table doesn't have to apply as much force up on the book to keep the book from falling through the table. So that means that there's lower normal force. If you're pulling up on something, there's less normal force. Less normal force means you take mu times n, that's going to be less, and that's the force of friction. So that's why when you want to pull something across carpet, it's good to lift up on it to pull it across the carpet rather than pushing down on it to pull it across the carpet. Some of those things that's kind of obvious, but it's good to keep in mind. I have two different problems with more Atwood machines. Remember these? Yeah, these are the multiple weights that are attached via a string, and that string goes around a pulley. And it ends up being a whole bunch of algebra, usually. But I've got two examples with a different kind of Atwood machine. And in one example, we've got no friction, and the next example, we see what changes when we add friction. So this one is a block rests on a table connected to a hanging block on a pulley. And I've got a drawing that I'll show you to help you understand. The block on the table is 4 kilograms, the hanging one is 7 kilograms. What is the acceleration with no friction? We've got a mass on a table connected to another mass hanging off the table via a pulley. There's a pulley right there. The first mass has 4 kilograms of mass. The second mass is 7 kilograms. We need to find the acceleration assuming that there's no friction. Remember, whenever you see a problem like this, where you're given forces and masses and strings and you're finding accelerations, you have to draw a free body diagram. More specifically, you have to draw one free body diagram for every object in your problem. we've got two objects in this problem that are going to be important. Each one of them needs a free body diagram. Free body diagram for M1. We can draw that here. M1, this is the free body diagram. There are three forces acting on it. Well, it doesn't want to fall through the table, so there's a normal force. Gravity, well, it's on Earth, so there's going to be gravity acting on it. Notice that I labeled it FG1 for the force of gravity on block 1. And then there's tension pulling along that string. This is going to be accelerating down, pulling this one across. And so you've got a tension there. Looking at the y direction, if we just take a moment to just look at the y direction, we can tell that the normal force is going to equal Fg1 because there's no other forces acting in the y direction. The normal force and the force of gravity have to cancel each other out. Otherwise, this block is going to start diving through the table or lifting up off into the air, and we know that those things are not going to happen. We can do this again with block 2. Block 2 is a little bit easier because the only forces acting on it are the tension pulling up on that string and the force of gravity pulling down on it. We can do one more thing as we are drawing our free body diagrams. We can make a note. This isn't really part of the free body diagram, but we can make a note of which way the acceleration is going to be in each case. In this case, the acceleration is going to be to the right. M1 is going to accelerate to the right. And we say that the right is positive. M2 is going to be accelerating down. That's pretty clear. M2 will accelerate down. We call down, or we define down to be negative. These are just definitions. It's just for our convenience. There's nothing special about these directions according to the universe. It's just, well, we've got to have something. We've got to define it some way. And so we define it as being right is positive and down is negative. So I'm just going to make those notes there. And remember that this M1 is going to have a positive acceleration, and this M2 is going to have a negative acceleration. Let's start by looking at M1x. This is the F equals ma equation for block M1 in the x direction. That's what this means. It also looks like the word mix. I don't know. So F net 1x, you see how quickly these subscripts just go wild. We started off with just F equals ma, and then suddenly, okay, F net 1x, 1x, oh dear. So many subscripts. Learning how to deal with subscripts and not be intimidated by subscripts is a very good thing. So pay attention to the subscripts, use them when you're working on your own problems, and it'll help you, I hope. Well, this is just going to be all of the forces acting on object 1 in the x direction, taking all the positives minus all the negatives. So object 1, all the positives. Well, the only thing that's positive is tension, and there's nothing negative. So this just becomes T. And we don't really know what to do with M1 or A1X right now. M1, I guess we know that it's 4 kilograms, but I'm not going to write that in yet. I'm the kind of person that likes leaving things as variables as long as possible, and then plugging in numbers at the very end. A1X, okay, I don't know what to do with that either, but I do know, now this I think is interesting. The acceleration of block M1 has to be equal to the acceleration of block M2. If block M1 moves 1 meter this way, block M2 has to move 1 meter that way. If block 1 moves 1 meter that way in 1 second, that means it's moving at 1 meters per second, then block M2 has to move down by 1 meter in 1 second, meaning it's moving at 1 meters per second. Same thing for acceleration. If this one accelerates at 1 meters per second squared, this one has to accelerate at 1 meters per second squared in that direction. So I can say that the acceleration of block 1 in the x direction is equal to the acceleration of block 2 in the y direction. Knowing, of course, that that's going to be negative, and we need to account for that negative. So what do? We move on to block 2. We say M2y because everything interesting happening to block 2 is in the y direction. So we have the net force on block 2 in the y direction is equal to M2, the mass of block 2, times the acceleration of block 2 in the y direction. One thing that I'm going to do here is I'm actually going to say that I'm going to define direction weird. And, I just said that we define down to be negative and up to be positive, but then I said right after that, but that's just arbitrary and we can do it however we want. I'm going to do a weird thing here, which you may or may not like. And it's okay. You can change it around very easily to something else. But what I've done is I've said here, down is positive. For this set of forces, I'm going to say down is positive. That actually lets me leave my acceleration to be positive, but then my positive force is m2g, is my mass times my gravity, my force of gravity. That's my positive force. My tension is my negative force in that case. So I get this equation. The other way of thinking about it, before anyone gets too confused by this, is you could do it normally and have up still be positive. And if up is positive, then you've got a positive t minus m2g. So I would just make this positive and this negative. And so positive t minus m2g, that would have to equal negative m2a. Because then I'd be saying, well, a is negative because it's going down. If up is positive, then this a has to be negative. So depending on how you want to think about it, you're either going to apply a negative to this side or a negative to this side. And it doesn't really matter because you're applying a negative. But if something is accelerating down, you'll either have to say, well, down is positive, and then it looks like this. Or you can say that up is positive, but my acceleration is negative because it's going in the negative direction. I can then replace a2y. If I've done it this way, I can replace a2y with just a and a1x with just a because they're equal to each other. So I can replace them both with just whatever, with a. And I give you a note here to note the direction. Anyway, I change those, and then I've got t is equal to m1a. That, well, I can just replace that t with m1a, and I get this. I've replaced t with m1a. I get this. I need to solve for a. Well, that's just algebra. Get all the things with a to one side, get all the things without a to the other side. Solve for a. I get m2 over m1 plus m2 times g is equal to the acceleration. And the acceleration is 6.24 meters per second squared. We can do the same kind of work that we did on the previous one to make sure that this equation makes sense. If m2 has no mass, if there's no mass here, then you get nothing for m2, and you just get 0, and so the acceleration would be 0. If you didn't actually have anything on that side, then this block shouldn't accelerate at all, which totally makes sense. If, on the other hand, you replaced m1 with a single atom of nothing, then that would go to 0, and you'd have m2 over m2, which would go to 1, so acceleration would be equal to the acceleration due to gravity, and it would just fall normally. So the equation makes sense. That's good. And we get 6.24 meters per second squared for the acceleration if you've got no friction. Now we're going to have the same Atwood machine, but with friction. The only thing that I've changed is I've given it a mu of 0.3. So it's a good thing we did the previous version first, so we can see how things work out without friction. Most of the problem is going to be the exact same, except we're just adding in one more force from that mu. So again, we set up the free body diagrams there and there the exact same way. The only change is now we've got a force of friction pulling back. The tension is pulling M1 forward. Friction is going to say not so fast, literally. And so we had to add that in. we know that this acceleration is going that way, so I'm being more explicit here, and I'm saying we're defining right to be positive, and I'm also going to say we're defining down to be positive, so that going down, any arrow that points down is positive, and any arrow that points up is negative for M2. Again, if you don't like that, you can just replace the acceleration for block 2 with a negative, and that says it's going down. Either way is fine. So if that's still bothering you, I very, very strongly recommend that you go to the book and you look at the Atwood machine examples. There's several Atwood machine examples in the book, which also explain that principle right there and explain how you can do that. I can see here that the normal is still equal to mg, and so I'll write that down there because there's no forces going, no extra forces going up or down. I can start working on m1x. You know, the only interesting stuff happening to m1 is in the x direction, so I started off the exact same way. I say that the tension minus the force of friction, because tension is positive, the force of friction is negative. Remember, net force, that's just meaning take all your positive forces minus all your negative forces. That's equal to m1a still. I can't replace tension with anything, but I can replace the force of friction with mu n, specifically mu k, n, again, m1a. I can replace n with mg, so I get that. And then I can solve for the tension because I know that I'm going to need it eventually, and I get that with a little bit of algebra. I can do the same thing on block 2 in the y direction. This ends up being the exact same thing that we had on the previous example. Noting the direction that I've used where up is negative and down is positive, you see there. And so the acceleration is a positive value there, just like in the previous example. I can plug this in for that tension, and that goes up here. I was kind of running out of room up here. I hope you can read that. But all this is I've taken this equation and I've replaced t with this expression. And I've remembered I need to put it in parentheses because the negative sign goes to everything. And so I apply the negative sign to everything, and I maneuver everything around. I need everything with an a on one side, so I add m1a to both sides. I need everything without an a on this side, and that actually accomplishes it right there. Then I can factor out m1 plus m2, or factor out a, however you think about it. I can factor out g and solve, and I get that the acceleration is equal to m2 minus minus mu times m1 over m1 plus m2 all times g. So you see, on the previous example, which was here, I'll leave this like this. Here's my new acceleration here. Here's my old acceleration there. The only difference is that this is new. That's the new thing. It was not up there. That term has leaped into existence, and it's a negative, and so it's going to tend to slow things down, make it less, have it less acceleration. And we see, if we plug in the numbers, that that is true. With no friction, you accelerate at 6.24 meters per second squared. With friction, 5.167 meters per second squared. So that's a different kind of Atwood machine, and we did that without friction and with friction.